Alright, Alex, so basically carrying where we left off, now you should probably full screen, let me know if it's still blurry, I can always read you off the values later. Again, if you need be. Basically, we have the circuit as drawn in the book. We have R1, R2, as well as R3, R4, and R5, and then we also have R6 over here on the right side as well. Now over here, this is where we found our equivalent resistance for the entire circuit. This is always nice for checking some of our work in the beginning calculations. Now we have our 1 over R plus 1 over R2. So yeah, 1 over R1 plus 1 over R2 plus our quantity of 1 over R3 plus 1 over R4 plus 1 over R5. Now that's raised to the inverse. Plus 1 over R6. Now that quantity is raised to the inverse. Then the inverse of the entire thing. This is basically the equivalent resistance that we found earlier, which was 8.229 for the second segment, and the total, which gives us 0.947. Now, the 0.947 allows us to calculate the total current in the circuit. Now, that's good for just summing up everything later. Now, what we found is that the total current in the circuit is going to be 9.507 amps. Now, we know that has to be distributed through the 3 different segments of the circuit. Now, in this circuit, we have 3 different parts that label the first 3 parallel sections of the circuit. The first one that we have is right here. Now that's pretty much just R1. The second one that we have is going to be R2. And then the third parallel leg is going to be this entire back section here. Now, within this back section, we do have a parallel set of resistors, and then we also have another resistor that's set in series with the parallel set. Now, to go about calculating, one rule of thumb, the thing with the largest resistance, the resistors, the largest REQ on this are going to get the least amount of current. The way to mathematically calculate that is knowing that the rule for voltages across parallel resistors is that the voltage across any given parallel resistor is going to be the same voltage drop for all of them. So since our 9-volt battery provides from A to B, where we have 9 volts at A and 0 volts at B, that means at the top section of R1 we have 9 volts and 0 volts. We also on the top section of B have 9 volts as well as 0 on the bottom. And that also means in the third segment that we're going to have 9 volts on top and then 0 volts on the bottom as well. So allowing this voltage difference, we can actually calculate R1, R2, and that third section. Now, for R1, we're just going to go ahead and calculate using Ohm's law, V being 9, I being unknown, and R1 being the given value, which is 2.3. Now, using that 2.3, we just substitute in, and then we can actually calculate the current in this first leg here. Now, I've already done the math for that, and that's going to be I1 equals 3.91 amps. For the second part here on R2, you do the same method, except instead of plugging in R1 resistance, you plug in R2 resistance. So that basically is going to give you 4.5 amps. Now, for the rest of the section, you're going to have a total of 9 volts across the entire thing. Now, what does that mean? Now, for the entire thing, you have a total resistance of 8.229 ohms, which is what we calculated earlier. So we can use that to actually find the total current across this piece as well. This will also be the sum of the currents, totaling, basically equaling the total current. So those are the two ways you can do it. Either take the total current and subtract the first two to find the third, or you can go ahead and actually do the other way, which is just mathematically doing the same thing that we did before using Ohm's law, V equals IR. Now, on V equals IR, make sure to use the equivalent resistance, and when you plug that in, you're going to go ahead and have your actual values for your REQ, which for this section is going to be 8.229 ohms, and that's going to be multiplied times the current for the entire section. Let's just label that I sub x, and then that's going to equal the voltage across the entire drop. Now the entire drop is going to be 9, and the reason that is because just like these other pieces, this is also in parallel, thus in 9. So for that, we just solve across for I. So we can go ahead and take 9 divided by 8.229, and that's going to give us 1.094. That's going to equal I sub x. Now, depending on rounding, it might be different, etc. for those reasons. So now that we know that this chunk here, which is going to be your R3, R4, and R5 resistors, are in series with the R6 resistor. Now, what that means is that the current that passes through the total, or the R equivalent, for this section here is going to also equal the current across R6. Now, combining this property with the property of voltage drops, we know that the voltage drop across this section plus voltage drop across R6 has to equal 9, because we have to go from 9 to 0 at the bottom. Now, since we know the current across the resistor, and we also know the resistor's actual value, we can use another manipulation of V equals IR, or Ohm's law, and just substitute in. So that's going to give us 9 divided by R6, which is 7.1, to give us a 1.267. So rounds up to 1.268. And that's going to be amps. Or, I'm sorry, whoops. Solved for the wrong thing, my bad. We're actually using the current that we calculated across R6, and that current is 1.094. And we're going to multiply that times the actual value of R6, which was given to us in the problem, which is going to be 7.1. That's going to give us 7.65. I call that V6 for volt across the 6th resistor. And that's going to give us 7.765 volts. Now, since we know that the total drop is going to be 9 to 0, so a total drop of 9, and we know that this drop is going to be 7.665 volts, we know that this must be the difference between the two. So the voltage drop across this 3 parallel resistors plus this one in series must equal 9. So using that, we can just take 9 minus 7.765 volts to equal, we'll go ahead and put units here on both, the total drop. So we just do 9 minus that answer to get 1.235 volts in total here as well. Now, we know that this is going to be the voltage across these 3 resistors. Now the voltage across any resistors in parallel is going to be the same across each resistor as a property, and the currents are going to split up accordingly, pretty much ranking themselves through different strengths of the actual resistors, which are going to allow it to be calculated through Ohm's law. So using this voltage, we can go ahead and calculate using V1, or the V that we calculated here, equal to the resistance, which we can go ahead and divide over. So depending on which R it is, whether it's R3, R4, or R5, we can go ahead and just do R3 here of 4.9. That's going to give us 0.252, and that's going to be our amps across that resistor. Now we do the same thing with the other one, so we have, once again, 1.235 volts. Now the rest of this is pretty much irrelevant, so you can go ahead and erase that. So we do the same thing here, and we just go ahead and divide by the same thing for resistor 4, which is going to be 2.0, and that's going to give us our current there, and that current is going to be 1.234779 divided by 2. So the I there will be 0.617. Alright? And then going on to the last one here, which is going to be 5.5 for that as well. So we just take that same value for the voltage, just divide by the new resistor value of 5.5, and that's going to give us 0.2245, and of course that's going to go ahead and just round up to 0.225. Okay? Now that's going to be the amps across the 5th resistor. Alright? This previous one being the amps across the 4th resistor, and this one up here being the amps across the 3rd resistor. Okay? So now we've just calculated all of the different I values for resistors 1, 2, as well as 3, 4, and 5, and then 6 as well. Now, in order to check the work, we can check to see using the properties again. We can see that R3 plus R4 plus R5, the currents across them must equal R6, because the currents across this sole piece must be equal. To the same thing with the entire circuit, R1 plus R2 plus this whole section over here in blue, that's going to also have to equal the total that we found earlier, which was approximately 9.5 amps, if I remember correctly. Alright? So, hopes this helps. Alright? Yeah. Fun math and physics. Do math.